So, single replacement reactions, you're responsible for predicting. I believe we'd covered almost everything on here, but we didn't predict all of them, right? We just predicted some of them. I'm going to take that as a yes, because my notes say that we did. So let's take a look at the one example provided here. You are responsible for recognizing that it's a single replacement, and then you also need to be able to predict the products. So if we follow our patterns, what we need to do is identify within our reaction the things that would exchange. What can you tell me about magnesium? It's a solid. Keep going. It's a metal. That's the one I wanted. You were right. It is still a solid. What can you tell me about nickel? It's also a metal. What can you tell me about nitrate? It is not diatomic. It's a polyatomic. That says atomic atom. So if we're going to initiate according to the pattern of our single replacement, we need to exchange the two most similar things. So we'll be exchanging the metals for each other, right? So we're going to pull nickel out, and we will put magnesium in. So far, so good? So, and where you might be saying no is that, well, you didn't predict the proper product, or it's not the balanced or correct formula for that product. I don't care about the formula yet. I just want to initiate the exchange. Okay, complete the reaction. I can then evaluate, are those materials correct? Does that make sense? So are we now okay that we've initiated the exchange? We've done that correctly. Okay. Are those products now correct? No. Okay, now where are our issues? So we take a look first at our nickel. Is anything wrong with that one? No, it's actually okay. Okay, we could go through and specify the phase. It is a solid. Then our single replacement, we're doing the full phase swap as well. Okay, at least superficially at this level. So the nickel needs to come out as a solid. Right? You should specify the phase, yes. The next one. What's wrong with that formula? The charges don't balance out. Magnesium is a +2. How do I know magnesium is a +2? That's one you either have to memorize or you recognize it off the periodic table. Okay? It is easiest for magnesium to lose 2 electrons to look like neon, so it's most likely going to gain a +2. Nitrate, what is the charge on the nitrate? It's a -1. How do we know that one? That is one that we have to strictly memorize. There's no pattern that we can look at. We just have to have that memorized. Okay? If we put that as our formula, 1 magnesium and 1 nitrate, the charges would not balance out. When you go through to predict your products, they must always have a balance of charge, must totals to 0. Hasn't totaled to 0. How do we fix that? I need 2 nitrates. Okay. Now what's the charge from the nitrate? Well, there's 2 of them. Okay. There was still only 1 magnesium, so I'd get +2 minus 2 equals 0. And that's what the charge needs to be when I predict my product. It has to come out to a 0 overall charge.
Why didn't you originally move over 2 nitrates at the beginning?
So, good question. And to answer that question, let's color code a little bit here. We're going to reference a green 2 and the black 2. Okay, so the green 2 is our magnesium with the nitrate. Our black 2 is the nitrate with the nickel. Okay. Why do we have a 2 next to the nitrate for nickel?
To balance out the
What is the name? So if we ignored everything, and I may regret this later, but I'm going to hope I don't. What is the name of that species? Okay. Nickel is a transition element, but that's not the name of that compound. The name of that compound, back to our nomenclature, would be our nickel. Okay, we have nitrate. So typically we'd call it nickel nitrate, and as Jeremy was suggesting, that is wrong because we're looking at an ionic compound and we have to specify the charge on our metal, okay? If it's not one we're required to memorize. Nickel is one we're not required to memorize. We have to specify the charge. So we need the Roman numerals. Okay, well, what is the charge on that nickel? How do you know it's a +2? Comes back to looking at our formula. There were 2 nitrates. Nitrate's a -1. There's a -2. There's only 1. X minus 2 has to equal 0. X has to be +2, right? Right? So the name of that compound is nickel 2 nitrate. So going back up to this, why is there a black 2 there? Okay, so our first suggestion, if we go back, see, I'll get you next.
No,
Okay.
I have to.
Our first suggestion was that it balanced the equation. Okay? Well, do you see an equation? No, and yet there's still a 2 there. Okay, so it can't be because of balancing the equation.
You know the charge of nitrate, and you know that's -1, and so you know that nickel is a +2 now, and so you can assume that there has to be 2 nitrates to balance
There
it.
are 2 nitrates to balance nickel's
nickel.
charge. That's why we have the black 2.
Yeah.
Okay, the black 2 is there only to make sure that nitrate balances out the charge on nickel. Okay? And this is where I said I might regret things, so let's see if I cannot regret things. At least not this. Wow, that's going pretty far back. There it is. Our green 2, because I think I went a little bit too far back. Our green 2, why do we have the green 2?
To balance out the nitrate with
To the nitrate to balance the magnesium. Is the green 2 the same as the black 2? No.
But the reason
They
is-
have entirely different meanings, even though the symbol is located in the exact same spot, in the exact same location. Everything else seems to be there, but they have very different meanings. The black 2 is because nitrate needs to balance nickel. The green 2 is because nitrate needs to balance magnesium. Okay? I cannot transfer the nitrate across. Okay? I'm not allowed to just say, well, that means I have 2 nitrates here. Okay? I have 2, and that's where students go, oh, well, you just transferred it across. No, there are 2 nitrates to balance the magnesium. Okay? Appearances can be deceiving. Yes?
So let's say instead of magnesium is lithium, and you only needed 1
So
nitrate.
we're gonna pause there, okay, for a couple reasons. Number 1, let's finish the question. Number 2, you're now making conjectures on something that we aren't looking at.
Yeah.
So we're now thinking entirely in our head. One of us is going to screw it up.
Okay, so maybe I'll change the.
So
So let's say for some reason you didn't need to have 2 nitrates in there.
I'm cool with that. We'll get to that.
Okay.
Let's
I'll
say
change the
magnesium
question.
has a
I'll change the
1.
question, but first let's address this one.
Or you can say for nickel. 'cause
Yeah,
nickel
we're going to
one-
address this one first. Okay?
Yeah.
Now that we've predicted our product, right, and we have our correct formulas, now we can balance the equation. How many times does each element show up on each side, and make sure it's balanced? Okay? That is practice that you guys should be doing. I'm not going to go through it for sake of time right now, but you should find that it balances perfectly. Okay? The last question that comes out of single replacements is, should this reaction actually occur? Okay? That statement is really asking, is that arrow valid?
And is it possible?
Okay. Is that a valid arrow? So what we've done is planned, if I win $1 million, this is all the stuff I'm going to buy. Now the question is, did I actually win $1 million? Okay? Kind of makes sense? So how do we decide, did we win $1 million? That now requires us to look at the activity series. Okay? The activity series will list lots of things within it, and depending on the extent of what we want to evaluate, it may have all of the metals on it, or it may have a very small subset of them. any list that we've got, the order will always be the same. Right? So what we're concerned about, not lithium, not potassium, not calcium. Why? They're not in our question. I'm concerned particularly about magnesium and nickel. Okay? There are now two approaches to how we look at this. So number one, or not the first approach, but magnesium and nickel. We need to be able to identify them on our activity series. We can look at them by looking at the most active or the least active, and hopefully we would get the same answer. Because if we get different answers, what does that mean? Something is way wrong with our question. Okay? So regardless of which one we look at, we'd better come to the same conclusion. So let's work through this. Magnesium is higher on the activity series, making it more active. Okay? If you are more active, you are likely to be around more people. Right? If you're less active, you're probably not going to see anybody. So being a more active species, I would expect to see magnesium with other elements. So I now look at my equation, the two sides, the left and the right. And I say, where is magnesium with other elements?
On the right.
On the right-hand side. Magnesium is chilling with nitrate. On the right-hand side, it's by itself on the, left. Okay? So what does that mean? Magnesium is more active. It looks at these two options. I can be by myself or I can be with people. Because magnesium is more active, what does it want?
To be with more people.
Be with more people, which happens to be on the right-hand side, which means the reaction should progress forwards, as shown. It makes sense to produce those products. Okay? That was saying magnesium was more active. Okay? So now let's look at nickel being less active. Because nickel is less active, what does it want to do? Be by itself. So we go back to the equation that we've drawn out. Where is nickel by itself?
On the right.
On the right-hand side, we come to the exact same conclusion. That conclusion is that, given the choice, I want to be on the right-hand side of this equation. Chemistry says products form, which means the arrow is correct as shown. Make sense? So you have to be able to interpret, is the word I was looking for, our activity series with respect to those metals. Yeah.
So metals can't be close enough on the activity series to where it could be true on both sides of the arrow? Like if nickel and iron are next...
So take a look at nickel and iron.
Yeah.
Is one still more active than the other?
Yes.
Yes.
But it
So
can't occur
the
the
way-
other direction, or it's just not, it's less likely?
What do you mean it can't occur the other direction?
Like iron can't...
Like iron wouldn't be by
lose-
itself?
Yeah.
Like iron wouldn't be where nickel is, the single replacement.
Is there ever an instance where the activity,
Doesn't match?
where the activity series doesn't actually work in real life?
No.
Okay.
Activity series works.
Okay.
Okay. So now let's see if I can come up with your question. We brought lithium in, plus we'll go ahead and use nickel nitrate again. Okay. Officially we'd have a box here because we don't know what to put in it. We're assuming at first that it goes to the products. We would do our single replacement. We'd end up with nickel all by itself as a solid plus lithium doing the exchange, whoops, with nitrate, right?
So there's going to be questions later on where it's like the box is there and you have to know whether or not this is...
What we just answered was identifying what's in that box.
Yeah.
Our first step is to assume it happens. Let's look at what the products are. Once we have the products, we can now compare reactants to products and decide was the arrow valid or not. It's really just asking true, false. Is that arrow correct?
Yes.
Okay. Everybody agree that we did the single replacement?
Yes.
Okay. So now the question is, did we do it correctly? Okay. Is our formula for nickel fine? Yes. Is our formula for lithium nitrate fine?
No.
What is the charge on lithium? +1. What is the charge on nitrate? -1. Is our formula for lithium nitrate fine?
Yeah.
Yeah. Why do I not bring the 2 over? What was the meaning of the 2? to balance nickel, is nitrate with
You're
nickel.
destroying metal.
No, you're not. Nitrate with nickel. No. So I can't keep the 2 with it. Okay? I have to be able to predict what my products are. Once I've predicted my products, now what can I do?
Balance it.
Now
So
I
you
can
put
balance the equation to ensure that I haven't destroyed
so
matter.
you put the 2 in front of the lithium nitrate.
Okay? And now for the sake of this, let's go through and work that out, because this one's not as trivial. We could go through and look at lithium. How many lithiums on left and right? 1 and 1, so it's balanced. Nickels. 1 and 1, that's balanced.
Oh yeah.
Nitrate. Did nitrate show up the same on both sides? Yeah, so I can balance nitrate. I have 2 and 1. That's not balanced. How do I fix it?
Put 2 on.
Okay, and this is where we have to be careful too, because a lot of people say, "Oh, well, I need a 2." No, you do not.
Put 2 in front of lithium.
Right?
2 in front of lithium, and then make it so there's 2
I
lithium
can't show
on the left
it.
side.
There's a 2 I wrote there.
Oh.
Just bring it forward. You can see it.
There you go.
Okay, I
There's a
didn't see
2
that
I
at
wrote
all.
there. If you're on that side, you can see it a little bit better.
No, you
Right.
put the 2 in front of the lithium.
I can't put the 2 there because then the formula for lithium nitrate is
Incorrect.
wrong. When I go to balance the equation, I can't change the formula. So I don't want the 2 there. I'll place the 2, whoops,
You didn't let me finish.
in front of it. That now fixes the number of nitrates. The instant you change a coefficient, what do you need to do? You have to loop back through and check your work. Because when you go back and take a look at lithium on the left, we have 1, but on the right, I now have 2. It's not balanced. What do I need to do? 2 in front of the lithium on the other side. Nickels. 1 and 1. Nitrates, 2 and 2. Now what do?
Check again.
You check it again. We changed a number. You got to check it again. Okay? Always. You change a number, check it. Okay? If you're tired of checking, what I will ask is change the number, you are required to check it again. If you do not change a number, you only have to check it once. Okay? Does that make sense? So we have to realize that when we go through to look at an equation, there's several parts that we're balancing. Okay? And this is that English part that we said was tricky. When we go to balance an equation, we have to make sure we've balanced our formulas first. Right? So there's balancing formula and then balancing the equation. Okay? And it's where we said balancing formula didn't make sense. We should call it evening or neutralizing, which we said also didn't work. Evening our formula. Once our formula is evened, then we can balance the equation.
Leveled? Balanced?
Not
No,
for me
you
to
don't
decide.
I like balance, I don't know what's confusing about balance.
Because I'm balancing the formula, then balancing the equation. I'm using the same verb to describe 2 entirely different actions.
Yeah, but that's
Because
why
of
you
that,
switched
it's
the word out.
true, but that's typically why people, like Braxton was suggesting, bringing the 2 across. And he shouldn't have done that.
So you wouldn't call it balancing reactants products and then the formula as the 2.
You're still saying balancing multiple times, yeah, and that becomes the confusion.
It's just balancing.
So the finished product, or the finished reactant
everyone
and
knew.
product, is it that whole thing now, the 2, the beginning, the reactant?
So
the
now
2,
our
the end?
overall equation is correctly shown and balanced. Now that's the whole thing. Yep. Questions about that? Okay. Why are we looking at single replacements before we move into redox? Okay. What is the charge on that structure, the lithium?
+2.
Plus 1.
Where is the charge always written?
Top right.
In the top right-hand corner, do you see anything there? No. What is the charge on that lithium? 0. There is no charge on it. Okay? And I can guarantee what's happening is you're saying, well, but lithium is supposed to be a +1 charge. Lithium is supposed to be a +1 charge when it's a cation in an ionic compound. Is lithium solid a cation in an ionic compound? No. None of those conditions are now true. You can't call it a +1. The charge is always specified. Right? Where it becomes tricky is that we could then look at the oxidation state. The oxidation state is something you must always calculate. The sum of the oxidation states for every atom within a structure, when added up, equal the charge. So if I take a look at that first structure for lithium, what are the atoms in that black box?
2.
Okay, we can run with 2, I'll accept that. 2 lithiums. The oxidation state?
0.
The oxidation state must always be calculated. You can't just tell me what that number is. It's unknown. What other elements show up in that black box?
Nothing.
Nothing. So I've looked at all of the atoms within it. That then must equal the overall charge in that black box. What is the overall charge in that black box?
0.
0. What is now the oxidation state for lithium?
2. Oh, wait.
0.
0.
0.
Being,
Okay. And you might say, well, that seemed like a lot of calculations to go through to do for something that we could have just said from the outset. Okay? The reason people are saying it from the outset is you're assuming charge and oxidation state are the same thing. The reason why I'm showing all this work is they're not the same thing. And I'm trying to highlight that differential. Okay? There are cases where they are identical. That does not make them the same. Oxidation state is the balance of protons and electrons in an element. Charge is the balance of protons and electrons in a structure. Can a structure be a single element?
No.
Yes. There's the confusion. Because the charge and the oxidation state at that point equal the same thing. What happened to the lithium through the course of the reaction? Well, let's jump to lithium in the product. Let's do the same process. What is the overall charge on that structure?
0.
How do you know it's 0?
Because there's nothing in the top right above.
We look in the upper right-hand corner. There's nothing written there. So the overall charge is 0.
Is it not a cation in this case?
Okay. We now have to go through and solve for the oxidation states for each of our elements. Okay. How many lithiums do we have? I'll accept 2. Times x, I have to solve for it. Plus, do I have any other elements?
Nitrogen.
I have the nitrogen. How many nitrogens do I have?
3.
1.
2. So
Yeah, because there's a 2.
let's address this because a couple people are picking up on this.
My bad.
Okay. The coefficient in front does multiply afterwards.
Yeah.
Does the coefficient change the balance of the atoms? No, because the 2 applies to every single one of them. Because the 2 applies to every single one, what could I do?
Factor it out.
I could factor out the 2. Right?
So the 2
It's
and
whichever is easier for you. So a lot of people were shouting 1 for lithium and 1 for nitrogen. That is technically true for solving this because they've already factored out the 2.
Yeah.
Which would you prefer to do? Factor it out or keep it in? Okay, I heard keep it in, so we're sticking with that. There are 2 nitrogens times their oxidation state, plus now how many oxygens?
6.
6. Good, everybody got it. Times the oxidation state. We don't know. I have to calculate it. Z. I now have one equation with 3 unknowns. What we learned from algebra is to solve for an unknown, okay, or solve an equation with 2 unknowns, I need 2 equations. Right? If I have 3 unknowns, I need 3 equations. 4 unknowns, 4 equations. 3 unknowns, 1 equation.
6 oxygens.
We aren't solving that anytime soon. Okay, so we need some extra information. Right? There's 2 pieces of extra information that we could apply here. Right? The first of which, Z, was what? The oxidation state for oxygen. Since you watched the video, you know that the oxidation state for oxygen is -2. Okay? So you could substitute that in. Great. Okay, for Z. That could work for us, but that gets us a second equation, still 3 unknowns. Still can't solve it.
2 unknowns if you know what Z is.
Okay? How can we solve for X and Y? So, Jeremy, you just said you've solved for X already. What do you mean?
Don't you have the lithium?
I have lithium in the reactant. Is lithium in the reactant the same as lithium in the product?
No.
No, that's why one's on the reactant versus the product side. So I still am in this boat of how do I solve this? Okay? Well, the solve comes from recognizing chemistry. What is the bond between lithium and nitrate? Like, we never talked about that. Yeah, we did. That's why you can name that compound, is because you know the bond. If you don't know the bond, you can't name it. It's ternary what? Ionic. It's an ionic bond. Because it's ionic, what can that species do? Split into the ions. And what I'm looking at there is not lithium nitrate, but it is lithium ion, which I know to be a +1, and nitrate ion, which I know to be a -1. That one box can actually split into 2 boxes. Can I now solve for the oxidation state for that first black box? Well, there's 1 lithium times its oxidation state, which I don't know, has to equal the overall charge. What is the overall charge in that first box?
1.
A +1. What is the oxidation state for the lithium?
1.
It's a +1. Okay. That was all I was trying to solve for, because that can get me to my next point. What happened to the lithium in the course of the reaction?
Changes oxidation.
It changed its oxidation state. How would it change its oxidation state? Okay? It would have to have lost an electron. By losing something negative, we by definition become positive. So we could go through and say that the lithium lost an electron. Lost an electron doesn't sound technical enough, so we added or invented a new word to describe what that process was. What is that process described as? I could say it was oxidized. Okay? Or my Leo. Okay? Well, if I was oxidized, if that species lost an electron, that electron had to go somewhere. It doesn't just float off into nothingness. Okay? That would be really weird if that was the case, because you'd be walking along and boom, you encountered an electron. What do you feel? The same thing you felt when you stick that fork in the electrical outlet. Okay? That's not going to be pleasant. Okay? Electrons aren't just free floating around. Okay? That would be a very awkward and uncomfortable experience. Okay? So they are confined, which means if this lithium lost an electron, something else
Gain 1.
had to have gained one. Now what was that something else? Okay? In that gaining, it would be a reduction. So what was that something else?
Nitrate.
Okay? That's where we could go through and evaluate the other elements and determine their oxidation states. Okay? We have the nitrate floating around. That is a possibility. How many people think we should look for the oxidation state for the nitrogen and the oxygen in nitrate? Why not?
That's like, it's not an element, that's a...
Nope. Nitrogen is an element. Oxygen is an element.
Them combined, what do you call it, a species not an element?
Them combined is a polyatomic ion. Does that mean the oxidation state for the atom can't change? It can absolutely change.
For the entire...
For the entire what?
What do you call
Compound.
it? Compound.
Okay, the entire compound, the oxidation state can't change. That's an invalid statement. Why is that an invalid statement? This guy, yeah. Oxidation state applies to what? Always. Nope, too vague. Or not vague enough, actually.
Oxidation state refers to like
The balance of protons and electrons for what?
Chemical.
No.
or-
For an element. Nitrate is not an element, but is nitrogen an element? Can I determine the oxidation state on nitrogen? Yes. Absolutely fair game. You were challenging me on that. Don't give me that. So with oxygen. Should we be looking at the oxidation state for nitrogen and oxygen from our nitrate? And that was back to the original question. Is that worth looking at?
No, because it can change.
If it changes, we just found what was reduced. That's useful.
Oh.
So guess what? Since you don't know, guess what you need to do? You get to figure it out. Set up the work, determine the oxidation state for both the nitrogen and the oxygen in nitrate. Electrons and protons on a single atom. Okay? Charge is the balance of electrons and protons in a structure. That structure could be a single atom. It could also be many atoms. So we have to be careful to not confuse them and realize that you're always solving for the oxidation state. But in certain circumstances, that solve is trivial. Like our lithium at the very beginning. It's trivial because you could do that internally. Okay? Very, very quickly just by looking at it. The nitrogen in your nitrate's a little bit harder. Okay? The nitrogen in lithium nitrate is even harder because you have to remember it's an ionic compound. I'm allowed to split that into the ions because it's an ionic compound. It by definition does that. Now that I have the ions, now I can go through and determine the oxidation state. I've simplified the process. Okay? So, back again to the original question that launched all of this out. Should we have even bothered with nitrate?
Yes.
Bothered what?
To determine the oxidation state for the nitrogen and the oxygen in nitrate.
No.
No. Why not?
Because
We're looking at nitrate. We're not.
Where's the question?
Nope, I can have the oxidation state change within that.
The nitrate's not losing or gaining electrons.
How do you know the nitrate is not gaining or losing electrons? The gaining and losing is now looking not at nitrate, but nitrate across the reaction. What did I start with? Nitrate. If I start with nitrate on the reactant versus nitrate on the product, what is the oxidation state for every atom within said nitrate? It's going to be the same, both on the reactant and the product. Looking at the nitrate is utterly meaningless because it did not change in the course of the reaction. If it doesn't change, don't look at the oxidation state. You're doing a bunch of extra work because all you're going to find is that, well, it didn't change.
Like this same element seems to be the same here.
Okay? And if it doesn't change, don't look for its oxidation state. So where should we have been looking for oxidation state changes? The lithium we already did.
Oh.
We have the nickel. Okay? We have no space to do this, but we'll try and cram it in here. The nickel nitrate is again what kind of bond? Ionic, so we can split it into the ions. And I have nickel with what charge? +2. Am I okay to call that nickel +2 with a charge?
No, it's a nickel
Yes,
2 ion.
I'm allowed to say that because it's coming from the ions.
Okay.
What is now the oxidation state on the nickel +2 ion? It's also a +2. Okay? Through solving your equation, x equals +2. If we move to nickel in our product, what is the oxidation state in that nickel?
0.
Okay? That one you're quickly doing in your head, it is 0. We went from a +2 to a 0. What happened?
Gain.
Okay? It had to have gained electrons because we went from a positive value to something more negative. If we'd lost electrons, we would have become more positive. If I lose negative, I become positive. Okay? And that confusion aspect has to do with the charge on an electron. Okay? Electrons are negatively charged, so when you lose them, you're losing negative by definition you become positive.
So lithium lost.
So
electrons.
lithium lost electrons, nickel
Gained too.
gained electrons.
So what do you?
Because it gained electrons, what type of reaction was that? That was our reduction.
And it doesn't have to
So-
equal out the
You-
First, Lauren? Oh, I
I
did,
was gonna
okay.
say, what do you want us to identify?
It's a different question, but yes, go ahead.
The electrons don't have to equal out yet.
Do the electrons have to balance out? Yes, absolutely. That's where we're hopefully trying to get to, is balancing electrons across a reaction. So kind of back to Lauren's question now that this is a complete disaster of work, okay? What could I ask about this? What are the products of this single replacement reaction? There's a question. What is the sum of the coefficients of the balanced chemical reaction? What type of chemical reaction is this? What species was oxidized? What species was reduced? How many electrons were transferred in it? All of those questions have been answered in all of that work. Buried deep within, but they're all in there. Lots of ways I can answer or ask questions about it. We can even go back to the original. Should this reaction have occurred? We'd have to look at lithium versus nickel, find out where they are. Lithium's at the top, being most active. Lithium wants to be with other elements. Where's lithium with other elements? On the product side, that reaction should carry forward as drawn, and I should have a reaction arrow going that way. Okay?
So what was?
Layers upon layers upon layers, and you can decide what those layers are.
We still didn't, because there wasn't an equal amount of electrons.
So we haven't addressed the balancing of electrons yet, but I would argue we need to make sure we're relatively confident on this, so let's take a break from that gory, detailed example and jump into our oxidation reduction. Okay? What I've got are several slides that are repeat slides from the video that you watched. They've got red titles because you've already seen them. Right? If you had questions while watching the video, this would be the time to stop me as I slowly, potentially fastly, quickly move through them. There's our big difference. Oxidation state applies to an atom. Charge applies to a unit. That unit can be an atom. Our oxidation state rules. Okay? Know the charges from your ionic compounds. That's because you can split ionic compounds into the individual ions. Okay? Oxygen will always have a -2 oxidation state, and the one that we've been using for all of our calculations is that next 3. Okay? The number of the element times the oxidation state plus the number of the next element times its oxidation state, so on and so forth till you've listed all elements within said unit. That must equal the overall charge. Okay? Charge versus oxidation state. You guys are good with all those? I'll say that's a yes, so we're just going to kind of jump through that. Oxidation states in reactions. If we look at our reaction, we'd have to look at the oxidation state for every element on both sides of the equation. What happened to the iodine? We went from a +5 to a 0. By losing electrons, we would become more positive. Going from a +5 to a 0, we became less positive. So we did not lose electrons, we gained electrons. Oxygen, -2 to a -2, nothing happened to it. Carbon went from a +2 to a +4. It became more positive. That was the loss of electrons. The next part is that loss and gain of electrons is too fancy of a word, or not fancy enough, and we introduce oxidation and reduction. The origin of oxidation, we noted that materials reacted with oxygen. When we got rid of the oxygen, the material didn't react. So we were like, oh, what happened was an oxidation reaction because it reacted with oxygen. Take a look at the top equation. Right? Which species was oxidized? Blue, color-coded, carbon. Carbon is bound to how many oxygens in the reactant? That would be the left-hand side of the equation. How many oxygens are bound to that carbon?
5.
There's only 1 carbon bound to the oxygen. There are 5 carbons. Each of those 5 carbons is bound to 1 oxygen. Okay?
Wouldn't,
Look at the formula as your interpretation. The 5 is to balance the equation, not the formula. Right? So there's 1 oxygen bound to the carbon in our reactant, in our product. 2 oxygens. We increase the number of oxygen bonds. That's why it's called oxidation. Reduction. What happened with the reduction? Reduction means to... Good answer. Try again. Reduction means to...
Reduce the amount of oxygen.
Don't define the word with the same word. How about get smaller, right? Right? Reduction. I'm reducing something, it gets smaller. Yeah? You got too much on the chemistry knowledge. Right? Must have been a lot of technology talk in the English class. Right?
It's pretty light day, it felt like.
Oh, okay. Well, we're making up for it. So let's take a look at the iodine. What happened to its oxidation number? It went from a +5 to a... What did I do to it? I made it smaller. I reduced it. Gain of electrons is reduction. The origin of our terms, oxidation and reduction, come out of what's happening with our oxidation states. Leo says Gur is my favorite. Believe it or not, oil rig is the most common definition that floats around for the mnemonic device. I find it very bizarre because it's usually the biologists that spew oil rig. Why is that a little bit ironic?
They don't include electrons in any of
Oil rig, what do we get from an oil rig? Oil, which is by definition long dead stuff. And what are they doing in biology? Studying living stuff. Like, you know, maybe a freaking lion.
Grr.
I don't understand. I don't understand. They got to do oil rig. Okay. Leo says Gur. If anybody asks, they tell oil rig, you can slap them and say, Leo says Gur is better. Don't slap them. That's mean. Don't do that.
Plus it says electron.
Okay. I would make an argument too. Oxidation is loss. I lost an arm. I must be oxidized. What? No. The electrons are the important part that we're looking at within these reactions, is how are the electrons transferred. Leo says Gur includes electrons in the mnemonic device. So here's a new one. Notice the black slide, right? The black title, right? You got those and you're like, oh, this is cool, right? I understand that. Oh, I had that slide up there? That was in the video?
No, I just remembered that cartoon.
Spy versus spy.
Classic.
So this, you're like, oh, I totally get it now. Now that we've talked about it for an hour, we're good. I get oxidation, I get reduction, I know how to identify them. That's phenomenal, that's fantastic. What do I introduce? I introduce an oxidizing agent. Look, who's coming through the door? Oxidizing agent. What would you expect the definition of oxidizing agent to be?
An element
Anything that causes
Maybe something that was oxidized, right?
an oxidizing agent.
But an oxidizing agent was not oxidized. Guess what an oxidizing agent did?
It oxidizes
The
something
oxidizing agent was reduced because
else. It oxidizes
it
something
forced
else.
something else to be oxidized.
So because it's the catalyst of it.
If I forced Greg to be oxidized, what had to happen to me? I had to be reduced. But because we're describing me acting on Greg, I'm also an oxidizing agent.
That makes sense.
Don't oxidize.
Sorry, that was all I could come up with. Right? So the oxidizing agents and the reducing agents are pretty much the opposite of what the word seems to say. Okay? Write it down on your exam, because the instant you try to internalize it, you're internalizing negatives and positives. I lost electrons and yet I'm becoming positive. What? Oxidizing agent, now I'm all sorts of confused. Write it down, simplify your work. So if you see ing or agent, that should cause a mild heart attack and cause you to look just a little bit closer. The other one to look for is ant, because sometimes you'll hear it referred to as an oxidant or a reductant. It's referring to the same thing as the agent. Okay? So watch out for those as definitions. Because I think you guys are rock stars at, oh shoot, we're just going to work through this one together because we got to do it. Sorry.
He still thinks you're rock stars.
I do still think you're rock stars, but we need to actually solve it. Okay? So to go through and do this, identifying the oxidation states, what we would start with is our copper. What is the oxidation state on that copper?
0.
What is the work for that?
X.
1 times X equals 0. The oxidation state is 0. What is the oxidation state for nitrate?
The oxidation state for nitrate.
The oxidation state for nitrate is what?
Nope.
A horrible question.
Horrible, yeah, so horrible.
Because the oxidation state applies to
Only an atom.
an atom. Is nitrate an atom? No. That was an invalid question.
+5 and -2.
Yeah, there you go.
I have 1 nitrogen with an unknown oxidation state plus, what do we have? 3 oxygens with an unknown oxidation state. This then must equal -1. Because we are rock stars, we all memorize that the oxidation state for oxygen is a -2. I can now sub in, sorry, -6 equals -1, and we get X equals +5. Everybody noticing that I'm specifying the positives and the minus whenever we talk about charge? Okay. I would always include those. It's redundant, but it's helpful to identify it.
That's oxidation, not charge.
What did I say?
Charge.
Oh, you caught me. You're right.
Gotcha.
This is the oxidation state on our nitrogen,
Yeah, it's just
not
for
the charge.
nitrogen.
And it's just for the nitrogen
Yeah. We already
in
knew the one for oxygen.
the nitrate. If we go through and look at our products, the oxidation state, oh, I
So
color
you
coded
can't make
horribly.
any, like, claims on the oxidation rate of, like, a compound?
Nope.
Unless it's a diatomic?
Can't make any claims about the oxidation state of any compound.
Okay.
For an element within a compound, absolutely. Even a diatomic molecule, you can't
It's
tell me
a
the
compound.
oxidation state on the diatomic. You
Yeah,
can tell me
of
the
each
oxidation
one.
state of each one.
Okay.
Okay? What is the oxidation state in the copper on the product side?
1 times X equals 2.
+2. X equals a +2. Oxidation state for nitrogen dioxide. Horrible question. Good follow-up. Our nitrogen. What was I, red for nitrogen? We have 1 times X plus
2y.
2 times Y equals 0. Why are you saying wait? Isn't NO2 nitrite?
Nitrate.
There's no.
Oh, wait.
Is NO2 nitrite?
Yes.
What is nitrite? NO2 minus. Very similar formula. What's the difference? The charge. Watch out for that. This is not nitrite. This is nitrogen dioxide. This is nitrite. The charge there is 0 because what is written in the upper right-hand corner?
Nothing.
Nothing. Yeah.
When it's alone, it will specify. When it's combined with another element, that's when it doesn't specify its charge.
The charge is always specified. Period.
Yeah.
There's
Even when the lack of there being the thing written
is
means it's a
specification.
0. Yeah, it's a specification itself. That means they're all 0.
Okay.
Yeah.
Yeah.
Yeah, and you may be like, well, that doesn't make sense. Sorry.
No, it makes sense.
Well, good. It makes sense. Let's just accept that, move on. What happened to our nitrogen?
You gain an electron.
Right. We gained an electron.
Then why do we have to memorize
Which
the
then-
atomic ions if it always specifies?
If I ask for the oxidation state of nitrogen in nitrate, you need to know the charge on the nitrate. If you didn't memorize it, you're
Gotcha.
dead in the water. Gain of an electron or gain of electrons to our nitrogen, which is what? Reduction. Which is what kind of agent?
Oxidation.
That is now an oxidizing agent.
So would the oxygen be the reduction agent?
Would the oxygen be the reduction agent? I don't know what happened to the oxygen.
No,
We
it'd
went
be the
from
copper. It'd be the
a
copper.
-2 to a -2.
That's
Did
what
it
I meant,
change? No. Okay? So we'd have to evaluate where we changed. We went from our copper to our copper plus 2. What happened? We lost electrons, which is oxidation, which is reductant. And I'm using the other term, the alternate term. Okay? The reason why I went through all of this, and yes, the next part, if we thought this was fast, the reason why is the next part's going to get even faster.
Just another word.
Yeah,
Balance
so
that.
oxidation agent is also oxidant.
It's just more name.
Balance that equation.
That we don't need.
Okay? Some of you are good at doing this internally in your head, so process through that a little bit for me. How many coppers on the left?
1.
On the right?
1.
1. Balanced, right? Can I balance nitrates? No, because nitrate doesn't show up the same on both sides. I get nitrate and I get nitrogen dioxide. Nitrogen on the left.
1.
On the right?
1.
Oxygen on the left.
3.
3 versus 2. Is that balanced? No. What could we do? Okay. We could try and balance it. This is where it becomes really ugly. We would need a 3 here
And 2 over there.
and a 2 there. That would then mean oxygens would both come out to 6, right?
Yeah.
So then we go back and check, and yes, some of you are already propagating out. We move the nitrogen, we'd be at 2 nitrogens versus 3, which also doesn't balance. So we would try and change the nitrogens. What would then not balance? The oxygens. So we change the oxygens, which then mean the nitrogens don't balance.
Yikes.
And you would continue that cycle indefinitely and find that there is no way to balance that. That is because you are missing information. Okay? We would need a lot more context. It doesn't change the oxidation state because the identity of the compound didn't change. Just the amount of that compound. Okay? So we need some more information behind this. This question in particular is a much more advanced balancing one. So we'll take a step back from this one as our exception. And what we'll do is take a look at, well, okay. Yeah. If you want answers, you can take a look at the answers. And now you're going to ask questions. It's going to make me stop.
You still haven't figured out why the electrons don't equal out.
What we're trying to evaluate is get to that. Okay? But we need a question that we can work with. If we try to balance this one, you should be able to balance this one, as I would call by inspection, by looking at it and recognizing we need a 2H+. The equation would now be balanced. So that is kind of a trivial reaction to balance. We can do that just by looking at it in our standard rule set. Nothing fancy beyond it. When we look at redox, we have to add an extra thing to look at. Okay? Here, we aren't recognizing it, so it's not super relevant to look at. So let's look at a new example. How many tins on the left? 1. How many tins on the right?
1.
1. Irons on the left?
1.
Irons on the right.
1.
Is it balanced?
Yes.
No.
Is the charge?
Because the electrons don't balance. What we also have to be aware of anytime we suspect a redox reaction is we need to balance the charge. What is the charge? Come back here. What is the charge on the reactant side? +5. Because both of those species contribute charge. I'm not looking at what species is what. I just want to know the total charge. What is the total charge on the product side? 6. Do those charges balance? No. This means somehow or another, I have, because I went from a +5 to a +6, lost an electron? Yeah. I produced an electron. And yet it's not in my equation, which means I destroyed matter. I can't do that.
So
Right.
Or maybe
So
it's like an incomplete.
this equation is not balanced. We now have to evaluate or use our redox knowledge to help us balance it. And it's looking at the charge to do that. Right? The textbook goes through and explains a method that if you understand it, by all means, teach me. I have no idea what the hell your textbook's trying to tell you. Okay? For this particular section. Okay? That's why when you look at your reading for chapter 17, it's just the first 2 sections. Okay? The balancing of redox reactions, they take to a whole nother level of difficulty. Okay? And I was already aware of 2 levels, and they were beyond that. Okay? So, how can we go through and balance this? Okay? This is going to require some adjustments to this. So what we're going to go through and do is take a look at half of the reaction at a time. If I can't balance the whole thing, I'll just look at pieces and hope that that can simplify it. So if I look at half the reaction, I want to pick one of my reactants. Okay, let's start with that. Tin plus 2. Should I try and balance by also adding iron plus 3? And now I want to balance that half of the reaction. What am I balancing it with then? Nothing.
Yeah.
That becomes very difficult to balance.
You just,
Reactant half versus product half. So maybe I want to balance
just the 2 tins and the 2 irons.
just the irons. Was it plus 4? Yeah.
And just the tin too?
Okay. That's 10. Whatever.
Whatever, okay. Should have that memorized.
You should have that.
Touche. And our irons. So now let's go through and balance these. Well, but our charge doesn't balance, and we don't know how to deal with that. Okay, because these are now half reactions, I have an extra trick up my sleeve. What is that extra trick?
Can you add more elements to make it so the charge is
I
balanced?
can't add elements. Nope.
No, so you couldn't make it like
Shock it.
Sort of along the line of shock it. By shocking it, what would I be doing?
Add electrons.
Adding electrons. What I can do with these half reactions, because they cannot exist on their own, they must be partnered with something, is I can balance each half reaction's charge with electrons. Tin plus 2 to tin plus 4. I have the same number of tins, but the charge doesn't balance. What I want to do is balance that charge by adding a charged particle, an electron. Okay? If I don't know where to place it, hopefully I'll put it in wrong, but let's see what happens. I'm just going to guess. I'm going to put in an electron on the reactant side. Let's ignore the tin for the moment.
on the product.
What happened to the charge of my products? Or that's my reactants.
So it'd be tin plus 1.
It would be a plus 1. Not a tin plus 1, it would just be plus 1.
Plus 1.
What is the tin on the product side?
Mine plus 4.
Plus 4. Did I balance the charge?
No.
Did I get closer to balancing the charge? No, I got further. What does that mean?
Wrong side.
I placed the electron on the wrong side of the equation.
So we have to do the product side?
So put the electron on the other side.
Oh. Fancy.
What's the charge on the reactant side now?
3. Oh, no, 2.
2 plus 2.
On the product side?
3.
Did I balance it? No. Did I get closer? Because I'm closer, I'm good. I'm now right on the right track. I just have to make sure it balances. How can I make sure it balances?
Another one.
Add another electron. I could go through and add a second term. It's usually easier if we just go through and say 2 electrons. Make sense?
Yes.
I can repeat that process with the iron. Okay? When I look at the iron, I'll only be doing 1 electron transfer. Okay? I think I heard your question. Give me a second.
Where are these electrons coming from?
If we add these 2 equations together, the net result would be an extra electron, right? An electron on the reactant, 2 electrons on the product. I can cancel those similar terms. Everybody good with that?
Yeah.
Okay. So that would now be better, at least balances the charge, but the issue is I've now produced an electron. Well, where'd that electron come from?
Another
Everything else
element.
is balanced, so that just kind of appears to be coming out of nowhere. Okay? If we then just say, well, it came from somewhere on the reactant side, okay, are electrons stable on their own?
No.
No. Can this reaction produce just a chill electron? No. This reaction is not balanced. Okay? Where did the electrons come from that I've put into my equation?
From the element.
Those came from the element, and it's typically easier to start with the oxidation one. Where did these 2 electrons come from? Those 2 electrons came from tin plus 2 becoming tin plus 4. For it to do that, what does it have to do?
Lose 2 more.
It has to lose 2 electrons. So if we start with the oxidation, it's like, I don't want these electrons. I'm going to get rid of them. For that to happen, though, the electrons have to be consumed because they can't just chill out on their own. So what happens is that the iron now says, ooh, you're giving up some electrons? I'll take one of those. That's where that 1 electron is coming from. It's coming from the 2 that were lost by the tin.
And
Right.
that doesn't equal up, then it's not.
And if that doesn't equal up, we're either adding electrons in that we don't have, or we're removing electrons that are unstable and can't exist on their own. And so the reaction doesn't work out. So when we go to add these 2 equations, the electrons need to be the same on both sides. How can I make sure that the electrons produced and the electrons consumed are the same? Balancing it how?
By the whole process that we just did, making sure that the iron and the tin are both equal on both sides.
But they are equal on both sides.
Yeah.
And the charge is even equal on both sides, but we're producing an electron. I need to make sure that the iron plus 3 consumes 2 electrons, not 1. Because 2 are produced by the tin. How can I make sure iron plus 3 consumes 2 electrons?
Do you now add elements or no?
I have 40 hamburgers. How can I make sure those 40 hamburgers get consumed?
Give them to 40 people.
I can eat 40 hamburgers?
You can try.
Ooh. How about I bring in some friends to help eat those burgers?
No, we said we can't.
How about instead of running 1 iron plus 3 to iron plus 2, I use
40 people.
2 of them.
40th of a burger.
If I now have 2 iron plus 3s, okay, how many electrons would I need to convert those 2 iron plus 3s? I would need 2 electrons to convert 2 iron plus 3s to not iron plus 2, to 2 iron plus 2s.
Yes.
Are the irons balanced on both sides of the equation?
Yes.
Yeah. Okay. What I went through and did is said that I want the electrons to be the same. The lowest common multiple between 2 and 1 is 2. I multiplied that equation by 2. Everything within it by 2. That changes the coefficient of the electron to 2. That changes the coefficient of the iron plus 3 to 2. And the iron plus 2 to 2. What does that do for me? Okay, well, we step through.
So why couldn't you just add elements in the beginning?
How do you know how many elements to add?
How do you know how many elements to add later?
What are we canceling?
The electrons.
The electrons. By doing the half reaction method, we can see what we need to cancel. If we don't have the electrons, can you see what you need to
What if you
cancel?
just set it up equally, so like for, I don't like diagonals, you just add the right amount of elements to the
So,
equation?
that's an interesting question. Could I just go through at this and say, well, the charges didn't balance initially, so instead of there being 1 tin and 1 iron, that I have 2 tins and then 1 iron. Could I have done that? Yeah, did that balance?
It does, yeah.
Yes. Without the
It does. So you
electron.
just need 1 iron.
Tin is what charge? 2. 2 of them? 4 plus 3?
7.
7.
2.
2 times 4, 8.
Oh, okay.
2. Did your charge balance?
No.
No. Was my guess correct? No. What do I have to do? Guess again. Guess again. Guess again. Guess again until it balances out. Or I look at the electrons to say, there's my
So
guess.
it is possible, but it's faster to do it.
Right? It is possible. It is possible on a multiple choice exam. Don't get me wrong. To say, I think the answer is A. Get the exam back. Whoops, no it wasn't. Can I change my answer to B?
But there is a way to.
Yeah, but it
be
doesn't
certain.
matter at that point.
You know, if you give it enough time, you could be certain.
Change the answer we
Well,
want.
you could do the quadratic equation too, but nobody wants to do that on every single
Yeah.
problem.
Okay. There's a process
say
that
no.
simplifies your work and understanding by balancing out the electrons. That's the intent of this. How many electrons were transferred in this reaction?
Losing the instructions is hard.
2. Okay? And because no one was listening to that,
I was too.
I know. So you'll be okay.
Oh, I should have took pictures.
Balancing practice. This will be a quiz on Monday. I want this equation balanced, okay, with the exam question, how many electrons were transferred? Okay? And in fact, we're going to make it a little bit different. I'm going to give you a piece of paper. You will write your name on that paper, and on Tuesday, I said Monday, didn't I? On Tuesday, you will give me that quiz paper within the first 5 minutes of class. We're going to change that. Within the first 5 minutes of the English class. Thanks. We're going to change that too. I don't want you working on that in English.
He's like,
In the transition between the English and chemistry classes.
that's great.
That is when it will be due.
So our break time?
During your break time. Oh my God, you're getting homework during the break time? No, you're getting homework right now.
To turn in during the break time.
Get the answer figured out so that when you come into class on whatever it is, Tuesday, there is no work. You just do it.